Okay, what we have here is a comprehensive simulation of the sun's motion. There's a lot of terminology associated with all this, and it's difficult to visualize how this all connects. I'm hoping to just kind of walk through this simulation a little bit with you, show you some of its features, and try to utilize some of this terminology in a way that hopefully makes some more sense. So here on the left-hand side, you'll notice we have sort of our standard view of our ground and horizon with a little stick figure, and you can see the sun is located right here. Now there's these two blue lines, and these are representing the equatorial coordinate system. So I have the first blue line here is the celestial equator, right? That's the extension of the equator out into space, represents zero declination. Yeah. And then here I also have they call it the prime hour circle, but this is basically the 0 point of right ascension. Now this point, I'll say this is the analog to the prime meridian on Earth's longitude, right? So this is 0 hours of right ascension. And it's really defined, this 0 point is defined by the sun's location on one particular day, right? And that's what I have it set to, which is March 20th. This is the vernal equinox, right? So the start of spring. I'll say what makes this an equinox, you'll notice. So there's a lot of things here. Here, we'll start with this one. Why is this an equinox? It's an equinox, meaning equal day and equal night, because the sun is located directly on the celestial equator. You'll notice that the celestial equator always passes the horizon due west and due east. So in this particular day, when the sun is located on this celestial equator, and the sun rises and sets, here I'll kind of keep going forward in time, we'll watch the sun set, that the sun will set due west. Right? So that means since it sets due west and rises due east, it'll spend exactly half of its day above the horizon and exactly half the day below. And we'll see that sunset's right about here at 1810. You can see the time of day right there. And so let me go back to where sunrise was a second. I'll grab the hour hand. We'll go back to sunrise, and you'll see that sunrise was at about, what we got here, 6:10, right? So 12 hours later would be 18:10, right? So 12 hours a day, 12 hours a night. So we have an equinox. Let's go back to noon. Okay, so there's our equinox. This is the vernal equinox because we're here in springtime. Again, that particular date defines 0 hours of right ascension. Now, of course, the sun doesn't stay in this location, right? The sun moves over the course of the year. And we can see the path of the sun by turning on the ecliptic. So I'm going to turn on the ecliptic right here. So what this is telling us, right, these are basically the constellations of the zodiac, right, would lie along this line. But this is the path that over the course of the year the sun will follow. And I can even see it the whole year by turning on the underside of our celestial sphere here. And we can see that this is the path it will follow all the way around. Now, that means as days go by, it's going to kind of move up and across on this ecliptic, right? But here's what's a little confusing about all this is on any single day, let's just watch how the ecliptic appears to move on the sky, right? As the single day goes by and the sun goes to sunset, right, the ecliptic kind of looks like it's changing its position on our sky, right? At sunset, you see the ecliptic's up here, and later on in the day, right, even later that morning, the ecliptic is low on the sky. So this can kind of be confusing at times, I think, just because it looks like so many different things are moving. But you'll notice here that when we get back to noon that we see the ecliptic kind of the same way, although the sun has moved a tiny bit over. And so what I'm going to do is I'm going to kind of step forward and we'll just kind of see that sun's motion, right? So I can step day by day here, and I'm going to do that. I'm just going to step forward 1 day, 2 days, 3 days, 4 days, right? Days are just flying by. And you see that the sun is moving across on that ecliptic. It looks like it's kind of going up in the sky. So let's just slow down a second here. A lot of things just happened. When I was going forward in time, right, you saw that the sun was moving away from my 0 hours of right ascension, right? The sun was increasing its right ascension, and we can even see that down below at the sun's right ascension. It's now 3 hours and 46 minutes of right ascension. So it's moved away from that 0 point. You'll also see that the sun's declination has increased. Again, this shouldn't be a surprise, right? If I rotate this back, you'll see this is sort of the view we had before, right? The sun was right here, the ecliptic, where the ecliptic meets the celestial equator and meets this 0 hours of right ascension. They were all right there, right? And now it's just following its path up the ecliptic, increasing right ascension and increasing declination. Okay, so wow, all right, a lot happened, but we're still here just at noon now. Again, it's in May. So I'm going to keep going forward in time. Now I'm just going to slide this bar up to about June 20. And you'll see this is the point where the sun has reached its highest declination. The sun's declination is about 23 degrees right there. Right? So the sun is at its highest point in the sky. Now here's what's interesting, right? This is the summer solstice, right? Solstice, these are the longest days of the year, and these are where the sun is shining down on the earth most directly. Now, I have just been going forward, right? I just went forward like 4 months. What I want to do is just look again at a single day, right? So I'm going to make the time again, just go forward during this day. Now, to make this a little less, well, I'll leave those markers on. So let's just go forward to sunset again, right? And I want you to notice where the sun is setting. Simply because of this higher declination of the sun, right? You'll see that the sun is now setting much further north of west, right? Much further north. And in fact, it rose. Well, let's check the time here, right? It's like 19 or almost 20 o'clock. So let's go back to sunrise now. And you'll see that the sun rose far north of east. So the sun rose in sort of the northeast, it set in sort of the northwest, and you notice the sun rose here at 4:30. It was up till about 20. So this was up, the sun was up for like 15.5 hours, right? So a much longer day, right? Hence that's why it's warmer. The sun's up for more hours of the day. That's why it's warmer in the summertime. Now this can allow us to visualize this changed path of the sun on a daily basis. This is where it's a little confusing, I apologize, but you see the ecliptic, right? That's the motion of the sun over the course of a year. But now in a single day, I just traced out this motion, right? I traced out this motion from sunrise to sunset. And I want to show that to you by turning on this thing called the declination circle. So you'll see, right, as I trace back again from sunrise to sunset, that yellow line represents the declination circle. So now, think ahead to where the sun is going next, right? As we go forward day after day after day, the sun will continue to follow the ecliptic, right, its path on the sky, and its declination will decrease. So this declination circle, presumably, will also decrease, right? And so let's check that out. I'm going to go forward again day by day. So here days are going to go flying by. And you see that declination circle, right, is coming down as well. So now, where are we? Mid-August, the days are starting to get shorter. Right, and we can understand that because the path of the sun over the course of a single day, its daily path, right, is getting closer and closer to that celestial equator where it's equal parts day and night. So let's keep going. And again, right here, boom, when the sun crosses the celestial equator, its declination is 0 once again. We have again an equinox, equal parts day and night, right? And we see this is September 20, so this is like the autumnal equinox, the start of fall. And we'll continue on, right? And now we're going to see as we approach winter, when the sun gets its lowest declination, we're at the winter solstice, and we'll notice that the sun is rising far south of east and setting far south of west. So the sun is up for a much shorter time. We can see here it's up only from about 7:30 until maybe 16, right? So what is that? That's like 9 hours instead of 12, right? So less time, less sunlight means it's going to be colder out. So we got our seasons connection there. All right, so there's a lot of different stuff that's showing on here. We'll keep it going forward so we get back to where we started, right? Right back up to the boom, vernal equinox. Okay, but I hope that connects a few things for you. In particular, I hope it connects this idea of declination, right ascension, position of the sun, to the idea of the equinoxes and solstices. We got the ecliptic in there, and we saw how the declination of the sun can make the day longer and shorter because it's making the sun rise further north or further south, meaning it's tracing out more distance on the sky. It's up longer to do that. Lots of stuff. Hope that made a little more sense. As you go through the lab activity, I think it'll make even more sense, and you'll get your hands on this simulation and do a little bit of it yourself.